In today's lecture, we are going to learn about improper integrals and how to deal with them. Basically, improper integrals are definite integrals that are not well defined. When you see this definite integrals, you know right away that we have a starting point at A and an endpoint at B. But this time around, these integrals are not well defined. What exactly does it mean by not well defined? Let's take a look here. It turns out that we have two types of improper integrals. Type 1 right here and type 2. Now let's take a look at type 1. It's when you have infinity or minus infinity or both for the starting, which is A, or the endpoint, which is B. So we are talking about these forms. Positive infinity as the endpoint, right here. Negative infinity as the starting point, or both negative infinity as the starting point and positive infinity as the endpoint. So the key is right here. Positive infinity, negative infinity, negative infinity, and positive infinity at the starting or endpoints. When you see this in your integral, you know right away that it's improper type 1. Now let's take a look at type 2. An improper integral type 2 is a little bit different in the way that the starting point A and the endpoint B, both of them are well defined. Both A and B. But the problem is the function itself, f of x, right here. That becomes undefined at some point between A and B. So this is the key. F of x becomes undefined inside this integral. For this undefined, we are talking about division by 0 or square root of negative numbers or log of negative numbers or 0. Now let's make a note up here for type 2. The starting, which is A, and the endpoint, which is B, are well defined. But the function itself, f of x, is undefined somewhere on this interval A to B. And once again, this is the key for improper type 2. And now to conclude, type 1 improper is all about infinity at the starting point or the endpoint or both. And type 2 is all about function becoming undefined at some point. As long as you know about this, you can tell which integral is regular and which is improper. Now let's take a look at some examples down here. In example number 1, we need to integrate 3 over x with respect to x from 1 to infinity. When you see infinity on your integral like this, you know right away that this is improper integral type 1. And this is what we do. We can't leave infinity on the boundary, like this. So we use a parameter and a limit instead. The key is right here, parameter and limit. Let's do that over here on the left hand side. We have an integral of 3 over x with respect to x. Starting from 1, we used to have infinity right here for the endpoint. But now we use a parameter b instead. Let's use b right here. However, that is not enough, so we use limit right here to tell this b to approach infinity. And after that, you perform the integration on this integral normally. And that is it. That is how you deal with an improper integral. So it's going to be equal to, and now we find the antiderivative of 3 over x. And we have 3 ln absolute value of x. And now we evaluate this at 2 values. The starting point, which is 1, and the endpoint, b. And don't forget the limit to tell b to go to infinity. And now we have the endpoint goes in right here. So we have 3 ln absolute value of b minus, now the starting point goes in right here. And we have 3 ln absolute value of 1. And once again, the limit to tell b to approach infinity. As you can see, this limit only applies to the front term because of b right here. The back term doesn't have b, so limit doesn't really matter. And now we have limit of 3 ln absolute value of b when b goes to infinity minus 3 ln absolute value of 1. Ln 1 is equal to 0. So this back term, the whole term, goes to 0. And this b goes to infinity. So now we have 3 ln of absolute value of infinity, and that is equal to infinity. So now we can say that this integral diverges to infinity, positive. In other words, this integral is divergent. Now let's move to example number 2. We need to integrate e to the power of 2x with respect to x, starting from minus infinity to minus 1. You see this negative infinity on your integral. You know right away that this is improper integral type 1. Again. And once again, we are going to use a parameter and a limit to replace this negative infinity. Let's work on that down here. We have an integral of the same function, e to the power of 2x with respect to x, from the starting point minus infinity. But now we use a parameter instead. Let's use a for that. To the end point, which is minus 1. And now we have this limit to tell a to approach negative infinity. And now we integrate this integral normally. it's going to be equal to. And now we find the antiderivative of e to the power of 2x. And we know it's equal to e to the power of 2x divided by 2. And now we evaluate this at two values, the starting point and the end point. The starting point is a, and the end point is -1. And we still have the limit to tell a to approach negative infinity. And now we have the end point, -1 goes in. So we have e to the power of -2 divided by 2 minus the starting point a goes in. And we have e to the power of 2a divided by 2. And now we have the limit. A goes to negative infinity, which only applies to the back term with a. And now we got 1 over 2e squared minus limit of e to the power of 2a divided by 2 when a goes to negative infinity. And we know that this goes to 0. So in the end, we have this 1 over 2e squared alone as the answer for this example number 2. We can also say that this integral of example number 2 converges to 1 over 2e squared. In other words, this integral is convergent. Now let's move on to the next slide. In this example, we need to integrate this function e to the power of x divided by 1 plus e to the power of 2x with respect to x starting from -infinity to infinity. When you see this negative infinity as the starting point and positive infinity as the end point, you know right away that this is improper integral type 1. With both negative infinity and positive infinity on the integral. And this is what we do. We split this integral into two integrals by choosing any point between negative infinity and positive infinity. So the key is right here, split into two by choosing any point. And this is how it's done. We have x-axis. So negative infinity on the left-hand side and positive infinity on the right-hand side. And now we pick a point in between, any point you want. I'm going to choose this one right here at x equal to 0. By the way, you can pick other values if you want to. You can pick 2, you can pick 10, you can pick 100, anything you want. By having this one point in between, I can have two integrals. The first one from negative infinity to 0, and the second one from 0 to positive infinity. So you can make a note right here that this is integral 1, and this is integral 2. So we start off with this integral of e to the power of x divided by 1 plus e to the power of 2x dx from negative infinity to positive infinity. And now we split this integral into two, equal to the first integral, same function, e to the power of x divided by 1 plus e to the power of 2x dx plus the second integral, same function, e to the power of x divided by 1 plus e to the power of 2x dx. The first integral goes from minus infinity to 0. This point 0 is the one that we chose on the right hand side, this one, right here. And now the second integral starts at the same point that we chose, 0. And it goes all the way to positive infinity. And now we have to evaluate these two integrals, this first one and this one, separately. And now let's take a look at the first one. It has negative infinity on the integral. It means that this one is improper. Type 1. And now on the second integral, we have positive infinity on the integral, which means that this one is also improper. Type 1. And once again, we use parameters and limits to replace negative infinity and positive infinity. So let's use a right here for the first integral and b right here for the second one. And now we have this. The first integral, same function, e to the power of x divided by 1 plus e to the power of 2x dx from the starting point, which is now a, the new parameter, to the endpoint 0, the point that we chose. And we have the limit at the front to tell a to go to negative infinity, plus the second integral, same function, e to the power of x divided by 1 plus e to the power of 2x dx. And now we integrate from the starting point, the point that we chose, and that is 0, to the endpoint, which is now a parameter b. And once again, we have limit right here to tell b to approach infinity, positive. And now we evaluate these two integrals, this one and this one. So we need to find the antiderivative of this function. Let's do that on the right hand side. For this one, I'm going to use substitution. For this one, I let u equal to e to the power of x. And I diff this du by dx, and I get the same function, e to the power of x. With this, I know that dx is going to be equal to du divided by e to the power of x. Now back to the integral. Same function, e to the power of x divided by 1 plus e to the power of 2x dx. Now that we know that u is equal to e to the power of x, let's use it right here. So this becomes u squared. And we also know that dx is equal to du divided by e to the power of x. Let's use it right here. And now we have this integral of e to the power of x divided by 1 plus u squared times dx, which is equal to du divided by e to the power of x. And maybe we got lucky here because this e to the power of x cancels with this one. And now we have integral of 1 over 1 plus u squared du, which is equal to, now we find the antiderivative of this term, 1 over 1 plus u squared. From the antiderivative formula, we know is equal to arctan of u. And since this is indefinite integral, we must have a constant c right here. And now we sub back this u equal to e to the power of x. And now we have arctan of u, which is equal to e to the power of x plus c. Now back to the left-hand side, the antiderivative of this function. E to the power of x divided by 1 plus e to the power of 2x is going to be equal to this term, arctan of e to the power of x. And it's the same right here for the second integral. And now we have this. First integral, we have arctan of e to the power of x evaluated at two values, starting point a and the end point 0. And of course, we still have limit when a goes to negative infinity, plus the second integral, and the antiderivative is the same, arctan of e to the power of x evaluated at two values, starting point 0 and the end point b. And now we have limit to tell b to go to infinity. And now we have the end point goes in, 0 goes in right here, and we get arctan of e to the power of 0 minus the starting point goes in right here, and we have arctan again, e to the power of a, and the limit at the front, a goes to negative infinity, which only applies to the back term, this one, with this a right here, plus the second integral. Now the endpoint b goes in right here, and we have arctan e to the power of b minus the starting point goes in right here, and we have arctan e to the power of 0. Limit at the front to tell b to go to infinity, which only applies to the front term, this one with b right here. Now e to the power of 0 is equal to 1. Same thing here, equal to 1. And now we have the first term, this one, arctan alone of 1 minus the second term with the limit. So we have limit of arctan e to the power of a when a goes to negative infinity, plus the next term, this one, with the limit. So we have limit of arctan e to the power of b when b goes to positive infinity, minus the last term, this one, and we have arctan of 1. This arctan of 1 cancels with this one. When a goes to negative infinity, e to the power of a goes to 0. When b goes to positive infinity, e to the power of b goes to infinity. And now we have minus arctan of 0 plus arctan of infinity. The arctan of 0 is equal to 0. And now the arctan of infinity, it's going to be equal to pi over 2. And now the final answer is pi over 2. So we can say that this integral converges 2 pi over 2. In other words, this integral is convergent. Now let's move on to the next slide. In this example, we need to integrate this function 1 over 4 minus x to the power of 2 over 3. Let's call it f of x. And now we need to integrate this function from the starting point 1 to the endpoint 4. At first glance, this integral looks fine because the starting point which is equal to 1 and the endpoint which is equal to 4 are well defined. From this, we know that this is not improper type 1. Now let's take a look at the function itself. F of x equal to 1 over 4 minus x to the power of 2 over 3. And now we can see that f of x, this function, becomes undefined when the denominator is 0. And that happens when x is equal to 4. Let's add right here that this function becomes undefined at x is equal to 4. And it turns out that this point, x equal to 4, is inside integration interval, which is from 1 to 4. From the starting point 1 to the end point 4. And the problem is right here at the end point. F of x is undefined. Now that we know that this function becomes undefined at some point inside the integration interval, we know right away that this is improper type 2. So we have this integral of 1 over 4 minus x to the power of 2 over 3. And now we integrate this with respect to x from the starting point 1 to the endpoint 4. And the problem is right here at the endpoint. Function f of x is undefined right here. And this is what we need to do for improper integrals type 2. We use a parameter and a limit to replace the undefined point. And the key is parameter and limit to replace undefined point. So we have an undefined point right here at x equal to 4. Let's use a parameter to replace that. Let's use b. And now we have an integral of the same function. 1 over 4 minus x to the power of 2 over 3. Integrate this with respect to x from the starting point 1 to the endpoint 4, which we used to have. Right now we have parameter b instead. Not just that, we also have a limit at the front to tell b to approach 4 from the left-hand side. So we have minus sign right here. And now we integrate this integral. let's work on that on the right hand side. For this one, let's use substitution again. So, sub technique is back. And now we try to simplify this, the denominator, and we have u equal to 4 minus x. Diff u with respect to x, we get minus 1. From this, we know that dx is equal to minus du. So we have this integral, 1 over 4 minus x to the power of 2 over 3 dx. And now we know u is equal to 4 minus x. Let's use it right here. So this becomes u. And this dx right here is equal to minus du. And now we have integral of 1 over u to the power of 2 over 3 minus du, which is equal to dx. Now let me move this minus sign to the front. And now I have minus integral of u to the power of minus 2 over 3 du. And now we find the antiderivative of this, u to the power of minus 2 over 3 is now equal to minus at the front, u, power increases by 1, so we have 1 over 3 divided by 1 over 3. So we have 3 at the front. As you know, this is indefinite integral, so we have a constant c at the end. And now we sub this back, u equal to 4 minus x to here. And now we have minus 3. U is equal to 4 minus x to the power of 1 over 3 plus a constant c right here. This is the same as minus 3 cube root of 4 minus x plus c at the end. Now let's move back to the left-hand side. At this point, we know that the antiderivative of this term, this function, is going to be equal to this term. So let's make a note right here that this is antiderivative of f of x. So let's use it right away. And we have this equal to minus 3 cube root of 4 minus x evaluated at two values. The endpoint is b and the starting point is 1. And now we still have this limit at the front to tell b to approach 4 from the left-hand side. And now we evaluate this. The endpoint goes in. b goes in right here. And we have minus 3 cube root of 4 minus b minus the starting point 1 goes in right here. And we have minus 3 cube root of 4 minus 1. And now the limit at the front. So that b can approach 4 from the left-hand side. This limit, by the way, only applies to the front term because it has b in it, right here. And now we have the limit of minus 3 cube root of 4 minus b. When b approaches 4 from the left-hand side, plus 3 cube root of 4 minus 1. This is equal to 3. For the limit, we know that b approaches 4. So b is really close to 4, about the same as 4. So this becomes 0. And the whole term becomes 0 too. And now the final answer is 3 times cube root of 3. And we can say that this integral converges to 3 times cube root of 3. In other words, it's convergent. And that is the answer for this example.